Okay, this is the second NetworkX video. So go back to the, I guess in Jupyter, go back to the folder that had the unzipped code in the starters folder. So next up, we're going to do distances. So click on that one. Okay, so we're working with the same network from before. So I'll go ahead and import NetworkX. I will import and then define this function that will read this graph from file. So in my case, I had saved it as my network.json. So, okay, I should be able to use this function. I will pass it the argument file name in my case. Appears it read properly. Maybe just to double check, I could go ahead and print the nodes and the edges. Okay, everything seems to check out. Okay, so to calculate distances, there are actually a lot of functions in NetworkX that can be used here. But I'll use something called shortest path length. And as argument, I'll pass first the graph, then I'll pass the source node. And for this exercise, let's find this distance from node 1 to all of the other nodes. So my source will be node 1. And so this will return a Python dictionary. And I'm going to call it dist for distance. And let's print it. Okay. So you'll see that from node 1 to node 1, its distance is 0. From node 1 to node 2, its distance is 1. So from node 1 to node 2, its distance is 1. But it appears that that can't be right. I mean, definitely the shortest path from 1 to 2 should have weight 8. So the reason that this is giving us the wrong answer here is because we haven't specified what the edge weight should be. So NetworkX is just supposing that we're trying to minimize the number of hops. So essentially just treating all of the edge weights as 1. So to make sure that we tell NetworkX that we should be using those edge weights, I should specify that the weight to use is the weight attribute. So with this JSON file that stores this network, it had stored the weight of the edges under this weight attribute. Okay, so if I rerun this, check. Okay, so from node 1 to node 1, the distance is 0. From node 1 to node 2, the distance is 8. But that seems more plausible. And then if you'll remember this from class, I think the distance from node 1 to node 8 was 32. So everything seems fine. Okay, so let's, instead of just printing this distance dictionary all at once, let's get the distances from 1 to each of the nodes individually. So for every node I in the keys of this dictionary, that would be 1, 2, 4, 3, 7, 5, 6, 8. We'll print the distance from node, I guess it's always node 1, to node I is distance to 1. Or distance to I, sorry. Okay, that seems to check out. You may notice that just because of the way that I think NetworkX is most likely using Dijkstra's algorithm here. So it's going to add the nodes to the dictionary, just like we did in class. So you'll see that these are sorted by their distances. And I think this is just a consequence of the way that Dijkstra's algorithm works. I don't think they're doing any post-processing here. This is just as the distance labels for these nodes become finalized, it adds it to the dictionary. Now, if you're curious what algorithm they're using or what the source code looks like, you can actually find that. So if we just type NetworkX shortest path length, Google or DuckDuckGo, you can actually find the code and find the other arguments. So we passed the graph. We said the source node was 1. We didn't specify a target node or a destination. We did specify weights, and we didn't specify a method, but it looks like the default is Dijkstra. Okay, so here are a whole bunch of other shortest path functions you can use and how we're using it. But yeah, if you're curious for the source, just click on source here. And here's all of the source code. So let's see what it does. So let's see. So in our case, so we did have a source. So this would not happen. So we did have a source, but we didn't have a specified target. So it looks like it's going to call something in here. And let's see, so method is question. So we didn't specify a method. So I think by default, it's going to use Dijkstra. So method is Dijkstra, so it's going to call this. And then, let's see. So it looks like it applies single source Dijkstra, and it wants path length. Okay. So in any case, if you're ever curious, you can always look that up. But the short story is it is using Dijkstra just like we did in class. Okay. So we have the distances from the source node to all the other nodes, but what if you wanted the actual path? So that we can also get. So we're going to use something called just shortest path. So again, the first argument is the graph. Then we need to specify our source node or our origin. And again, we want to be using these weighted edges. So the weight should be the weight attribute. Okay, so this will return a path dictionary. So I'll save that to path, and then I'll print path. Run that. Okay, so a shortest path from node 1 to node 1 is just 1. Shortest path from 1 to 2 goes 1 to 2. And then let's say the shortest path, or a shortest path, from 1 to 8 is 1, 3, 5, 6, 8. And let's see, 1, 3, 5, 6, 8. So that's 15 plus 6 is 21, plus 7 is 28, plus 4 is 32. So I think that's exactly what we had seen in class. Okay. So that's all one big path dictionary. We can also print this out for each node specifically. So for every node I in, I should say path.keys, is that a shortest path from node 1 to node I is the I. Okay. So this will work if you want the shortest path from one node to any collection of nodes. So you can just find all of these paths and then just query the specific one that you want. But if you're working with a really large graph, this path dictionary can be quite large. So if you think, for example, of I'll draw something here. So think of a graph that goes 1, 2, 3, 4, 5, and so on, all the way to, let's say, I don't know, 1 million. If you get shortest paths from node 1 to all other nodes, the paths would end up being 1, 1 to 2, 2, 3, and so on. And then that very last path going from node 1 to node 1 million, like that. So if you look at the amount of space that this is going to take up on your computer, it's quite substantial. So it's essentially the size of this is going to be 1 plus 2 plus 3 plus and so on, all the way to 1 million. And this is very large. So this is going to take up a lot of space on your computer. So if you're working with a 1 million node graph, this path dictionary could be huge. And if you don't need the path from, if you don't need the paths from this node to every other node, maybe a quicker way to do this is just to get this shortest path specific to your origin, your destination. So this would actually be the same that we did before, but now I'll just need to specify that the target node is 8. If I run that, it'll give me just that single path. So even if you had this 1 million node graph and you're trying to find the shortest path from 1 to node 1 million, it's just going to be 1 million nodes. Whereas this, I think, is going to be, I think this would be n times n plus 1 over 2. So what does that come out to? I think that's 500 billion. Okay, so that would be huge. Your computer would not be happy with that. Okay.